Now let's take a look at treating an epoxide doing a reaction under neutral or basic conditions. And what we're going to do is we're going to open up this ring and form an alcohol. Now what I have here in the middle is that I'm going to take this epoxide and react it with this reagent and draw the product. And then this one. And you see how it's color coded here? So if we look at this pink one right here, in order to do this transformation with lithium aluminum hydride or sodium borohydride, we have to do it in 2 steps. So this 1 and 2 is just one idea. And then here in blue, that's one reaction scheme right there. So we're going to look at all those separately. But the mechanism is very similar for every single one of these reaction conditions. Okay? And if I could just generalize it, what would happen is if we have this epoxide, okay, this one right here, let's draw it like so. What's going to happen is you'll take these reagents here, and I'm going to represent those reagents just a generic R, okay? An R minus. So we'll put on some lone pairs right there like so. Okay? So this R right here could represent the chloride, or it could represent the methoxide piece, or it could represent that piece, or that piece, that piece. In this one, it would be just the hydrogen. So I'll put that in parentheses. That's just going to add a hydrogen. There, okay. So this R minus right here could be represented by that H right there as well. So the mechanism, let's see how it works here. We'll take the R minus. It's going to come in and attack the carbon. When it attacks that carbon, it's going to break this carbon-oxygen bond right there. Now remember, there's already 2 lone pairs on that oxygen. We're going to break it like so. Okay. And so that will bring us down to here. What was that first mechanistic step? That was a SN2. Now when we open up this ring, what I want you to do is we have carbons 1 and 2. I want you to just draw those carbons. See how it's just that horizontal bond right there? Just draw the horizontal bond. We notice that this carbon-oxygen bond right there is broken. But we still have an oxygen-carbon bond between to carbon 2. And that stays on this side. We have the top face of this bond and the bottom face. So bottom, top. We see that the oxygen is on the top face of that single bond there. But it already started with 2 lone pairs, and now we put another lone pair on there. So that makes that negatively charged. Now this R group has come in from underneath the ring, or underneath that single bond. And why am I invoking it that way? Because it's an SN2 mechanism. So it has to come in side attack. So if this carbon-oxygen bond right there is the leaving group, then the nucleophile or attacking species has to come in backside. And so that came in from underneath that single bond there. And then we would have one more step, and that would be a proton transfer. And so that proton transfer can occur in a couple ways. In this example here, and this one, and this one. Okay. So let's highlight that again. So for this one, that one, and that one, the proton transfer is going to come from the solvent. So if this is methanol, we could draw our methanol here, like so. And so the proton transfer would simply be the electron-rich alkoxide is going to come in, grab that proton in a proton transfer fashion there, and make our product. And what would our product look like? And I'm going to draw it right here now. Our product would be that. So that's our starting material. That is our product. Okay. Now, this last step of the proton transfer is going to be different for this reaction, that reaction, and this one. And you can see what's different about those last three is that you have to have this second step right here. That's where the proton transfer step's going to occur. So for this one, we see HCl, and so we would just replace it right here, that when you have HCl in water, you're going to generate what? The hydronium. Right there, there's our hydronium, and so this would come in and grab the proton like that, like that. But one thing to highlight here is that every single one of these is under neutral or basic conditions. So let's highlight that. So this reaction right here is a neutral condition. There's no base present. This one is under basic conditions because we have that negatively charged oxygen right there. That's a strong base. This one right here, yes, there's two steps. We're not too worried about this second steps right here because that second step is a aqueous workup or a acidic workup. It's just that step 2 is just to do the proton transfer. So when we're classifying these reactions, are they neutral or basic, we're looking at the first step. And the first step we can see is a alkyl lithium reagent, which is basic. In this green one right here, we have an R group or a Grignard, so that's basic. And then our lithium aluminum hydride here, that's going to be, let's see, with lithium aluminum hydride or sodium borohydride, we'll call that just neutral. Okay. So let's just take a look at each one of these steps or each one of these conditions and show you what the product actually looks like so you can have a general idea of what's going on here. But this mechanism right here is the same, very similar for all of these here. So let's look at this first one. What would our product be? That would simply be, hey, that right there, our chloride, that's going to be the R group. So that would just be a Cl. This one right here, well, that's the attacking species. So that'd simply be what? The oxygen would be the nucleophile, and that oxygen atom is attached to a CH3. And that's cut off. You can't see that. So let's just make this molecule a little bit smaller here. There you go. Okay. So that's what the product would look like for this guy. When we have the alkyl lithium reagent, we would just add 2 carbons, 1, 2. So 1, 2. Because remember, that's carbon 1, that's carbon 2. That's what we're attaching. We're attaching to carbon 1 in this example here. If we use to look at this Grignard reaction right there, what would our product be? It would just be that R group right there. Sodium cyanide, what would that one be? Sodium cyanide. This one, lithium aluminum hydride or sodium borohydride. Remember, lithium aluminum hydride looks like this. is a hydride. So that aluminum hydrogen bond right there is very nucleophilic. And so we are just adding a hydrogen. So to carbon 1, we are going to be adding a hydrogen atom for that reaction. Okay. So pretty slick. So in the next video, we're going to take a look at how do you open up an epoxide ring when, let's say, you have a substituent on one. So that, let's make that a methyl. So these attacking species, or these nucleophiles and hydrides, when you have an unsymmetrical epoxide, does it attack carbon 1 or carbon 2? Okay? That's what we're going to look at in the next video.